There we go. So always remember when there's division, you gotta check if there's any additional issues with the domain of A intersect B. Okay. They're going to ask you to do this stuff graphically as well. So I've got some graphs here. Now I've made this I wanted to make this a little bit more interesting, so I made this into a piecewise, so that I've really got three functions here. G of x is actually a composite of two functions that I call G and H. But regardless, we should be able to do this. The questions that they're going to ask you graphically, guys, are going to be kind of this nature. They're going to say, find something like f, and they can use any operation, so I'll just use addition here to make it a little bit quicker. They might say find f of 1 plus g of 1. So we'll write it this way, which to us means exactly the same as f of 1 plus g of 1. So what am I doing here? What is f of 1? What do we call that? 1 is an x value. What's f of 1? It's a y value, right? We're adding outputs here. So what is f of 1's output? Or value, f of 1's value. F of 1 is that y value of 1. What is g of 1? Negative 1. So then f plus g of 1 ends up giving me 0, right? Okay. So I'm going to actually plot some of these points here that we go through and find. Okay. What if I ask for f plus g of 0? Well, that's f of 0 plus g of 0. So f of 0. What's f of 0? 2. What's g of 0? 0. So this gives me 2 plus 0, which is 2, right? Okay. Now the idea, guys, is once you're able to find those f of whatevers and g of whatevers, it doesn't matter whether I'm adding them, subtracting them, multiplying, or dividing. If this was f times g of 1, you would take 1 times negative 1, right? If it was f times g of 0, you would take 2 times 0. So whatever the operation is, we should be able to do. Plot this point, 0, 2. Okay? What's going to happen, guys, is eventually they're going to ask us to maybe fill in what this graph will look like. I believe, and we'll come back to it in a moment, that this graph actually kind of looks like that right there. So that dotted line would be like your f plus g of x graph, okay, between 0 and 1. What if I asked this question? What if I said, what is f plus g of negative 1? Okay, what's g of negative 1? G of negative 1 is 1, right? What's f of negative 1? Undefined. So what amount do I have when I take an undefined and add 1 to it? Still don't know what it is, right? Still undefined. And that's the idea, guys, that you're only going to get an f plus g where the domains of these two things overlap. Does that make sense? You're only going to be able to add y values where the two graphs overlap in regards to their x's. So I can only add between 0 and 3. Does that make sense? Yeah. If I ask for f of 4 plus g of 4, I get the same issue that I had right there with f of negative 1. Let's do one more here. Let's go f plus g of 2. F of g, or f plus g of 2 should give me y value of 0, y value of 2 should give me 2 back, right? Okay. If I do 3, f of 3 is 1. Sorry, f of 3 is 5. G of 3 is 1, so it should give me 6 back, right? Okay. So let me just kind of show you what graphically this would look like if I started adding these together. So f of x plus g of x. Okay, so it looks like that little orange curve. So So the way I've got this written in the background, to actually get the rest of this from 1 to 3, I'm actually having to take, because this little linear part here was actually h instead of g. So I'm going to call f of x plus g of x, f of x plus h of x. Gives me that one. So this, let's go. That purple curve, guys, is if you were to sit down and find like all those x values between 0 and 3 and evaluate all of them at f plus g. Does that make sense? Okay. Notice that it's only defined between 0 and 3 because that's the domain of the original two functions. Now, if I did, we can do all kinds of things with this. We're going to go f of x times g of x. Okay, and then I had f of x times h of x. So if I do the product of the two functions, it should give me that black thing. Does that make sense? Is it still only defined between 0 and 3, though? Okay. If we go f of x minus g of x, and then go f of x minus h of x. Okay, so if I do the difference of these things, it's going to give me that black curve. Does it still exist only between 0 and 3, though? Okay. So the version of these graphs, the visual of these graphs is going to be different, but the domain, no matter what I do, add, subtract, multiply, divide, is still going to be between 0 and 3 because that's the only place that the blue function and the red function are defined together. Okay.
Where'd you take that down?
Take what down? Oh, that sign? Gravity. All right. Talk about one more. So that's combining functions. That's combining functions. Now we'll talk about composing functions. Okay. Which is something we've already done. But I don't know if you, you did it in Algebra 2 completely. We've also done it in this class already. But I don't know if we observe it as a composition of functions. Here's what I'm talking about. You guys remember taking, let's say f of x is equal to x squared plus 3x. And then I said find f of a plus h. And all you did is you found the x, and you replaced it with a plus h.
Yeah.
And you found your your x here, and you replaced it with a plus h. Remember doing that?
Yeah.
Okay? That's a composite function. Okay? That is, let's kind of translate that over to the notation that we're going to use. Let's say f of x is equal to x squared plus 3x. And now instead of calling this f of a plus h, I'm going to call it g of x. And instead of using a plus h, let's just use x plus 1. Okay? Still kind of the same structure. Okay? But now what I'm going to do is I'm going to take this thing here, and wherever I see an x up here, I'm going to replace it with x plus 1. So it's going to turn into x plus 1 squared plus 3 times x plus 1. My hope is that you can see that those two things are kind of a similar approach of work, right? Does that make sense? Okay. Now, what I'm going to say is that on the left-hand side, when I have f of x and f of a plus h, if we view a plus h as a separate function, a new function, different than x, or different than x squared plus 3x, then we have what we call a composite function. This is two functions. The way we would write this is that we would say f of g of x. Okay, that's the notation. Maybe you've seen that last year, and maybe this will make it jump off the page a little bit more. Last year, maybe you've seen it written that way. You guys remember that? That open circle?
Yeah.
Okay. That open circle stands for the word composite, okay, or composed with. So f composite g of x is the same thing as f of g of x, okay? And really what this means, guys, is that we're going to take whatever that innermost function is. You hear me say that word, innermost function. It's the one that x is attached to. And you're going to substitute that into the function that it is inside of. So it's inside of f. Does that make sense? So I take g, which they said was x plus 1. And I'm going to substitute that into f of x. So my g of x, that function, becomes an input value inside another function. Is that okay with everybody?
Yeah.
So and that's what it means by a composite. It means a function becomes the input in another function. Okay? Kind of give you a graphic real quick of what composite functions are doing. Actually, I'll let you maybe write the definition down first, if you need it. Okay? I think this is the key thing here, is to be able to recognize that those two structures are the same, those two notations are the same. I hate the one on the left. Okay? When I was in school, I looked at that. Fog, what's fog mean? I have no idea. Okay? What I want you guys to be able to do, what makes, I think, easier to realize what is being substituted, how many times you're doing it, all that kind of stuff, is that you work from your left to your right. And I'm going to say F, and then I'll put a parenthesis, and now I put G, and then I put a parenthesis, and the next thing I see is X. So I write it that way. And then I realize, well, once I see that I've written X, now I just need to close all the open parentheses. So I close those open parentheses. Now you might say, well, that's not necessary. I understand what's going on, and that's fine. But I think the issue for a lot of people comes when they start seeing something like this. F composed of G, composed of H, composed of W. Oh, not a composed. Composed of W. Of X. And then they start thinking, what in the world is going on here? Well, if I go left to right, just like I said, okay, start with F, put a parenthesis, then it goes to G, put a parenthesis, goes to H, put a parenthesis, goes to W, put a parenthesis. What's the next thing I got to write? X. Now, once I write my X, I then go and close all open parentheses. So there's 1, 2, 3, 4 open parentheses, right? So I got to close them all up. Okay? The only thing here, it's more steps, but the only thing here, guys, is that we work for the innermost function. So the one with X is our innermost function. And that means W of X is going to become an input for which function? H. Okay? And I'll evaluate that. Does it make sense? I'll figure out what that is. And then that becomes the input for what function? G. And I'll evaluate that, figure out what that is. And that then becomes the input for what function? F. Okay? So you work from the innermost function, kind of systematically using that object as the input for that function, either W, H, G, or F. Okay? And the idea here, guys, is even this. Let's say that, and let's just go to a specific, let's just say F of X is equal to 2X, and G of X is equal to X cubed. If I ask you to find F of, let's write it this way, F composed of G of X, that becomes F of G of X, right? The first idea is that you're going to take X and you're going to place it in what function? Think about this. Think about this. Maybe is the way most people are going to do this, but logically, that's my first input, isn't it? And I'm going to go to G, and we'll plug it in for the variable in G. Well, what if I plug X in for X here in G, what do I get? X cubed, right? So most people are going to kind of circumvent that and say, oh, well, the innermost function is just G of X. So I replace the yellow with what G of X is. Does that make sense? But the idea is that first you're taking X as an input, running it through G, and what do you get? Well, you get what G of X was. Okay? Now, what's it say to run through F? X cubed. So now I'm going to go to my F function, and wherever I see my X, I'm going to replace it with X cubed. So I get that thing there. Does that make sense? Okay. Well, what if I did this? What if I go and ask the question, G composed of F of X? That would be G of F of X, right? Okay, I take X and plug it into F, and that's going to give you 2X, right? So now I'm looking at G of 2X. And now that becomes my input for G of X, right? So I'm going to replace that X right there with 2X. And what's that turn into? What's 2X cubed? X cubed, right? Take the 2 and cube it, take the X and cube it. Okay. Now here's my question. Are composite functions commutative? No, not always. Okay. But here's kind of what's going on here. If I take, let's just say an X value. Okay. And let's run that X value through a function. Give me a number.
7.
I heard 3.
What? No.
Well, I don't want to cube 7. Okay? So it takes 3. And let's run that through our F function. So what that's going to produce is some value over here, which will be now an output for F of X. Does that make sense? So if I take 3 and run it through F of X, what do I get? 3 run through F, you get 6, right? Okay. Now, the whole composite idea is that you're going to take that output now. Because think about this, and we're doing this one right here. Okay? We evaluated first that F, right? Evaluated F at 3 first and got 6 back. Now you're going to take that 6. So that becomes G of 6 now. Does that make sense? So I'm taking this output, run it through another function G, and now what does 6 times 6 times 6 look like? Should be 216, I think. Okay. 6 cubed, is that right? 216? 36 times 6? Yeah, okay. And that's my final output. That there is then G of F of X. Or it's my initial output of 6 evaluated as an input value inside of G. Does that make sense, everybody? Now let's think about this. What would be quicker? What would be quicker? Couldn't I take this 3 and run it through that right there? Okay. What's 3 cubed? 27. What do we got here? Hold on a second. Am I looking at the right one?
You mean
Oh, yeah, I'm sorry. We're doing 8. I'm sorry. I circled the wrong one. That's what I was thinking. That one. There we go. What is 3 cubed?
27.
27. And then multiply that by 8? 216. So that allows me to go straight from there straight to there. Does that make sense? Now you might think, well, what's the purpose of that? Because I could do 3 evaluated at 2x and get 6, and then 6 evaluated at x cubed and get 216 and not have a problem, right? You guys agree with that? I mean, that's not, in terms of efficiency, all that terrible. The purpose of being able to create x cubed is when I have all those additional points. Maybe I've got 12 points in there. Do you want to evaluate 12 inputs into f of x, get 12 outputs? Take those 12 outputs, run them through G, and get then final 12 kind of G of f of x's. So you would do 24 kind of operations there, right? Or 24 evaluations. Where if I just start with x, those 12 x's, and run them through 8x cubed, I only do 12 evaluations there. Does that make sense? So it should cut my time in half if I have multiple input values that I'm trying to evaluate from. Okay? So that's the idea of what composite functions are doing. They're allowing us to kind of skip over algebraically this first output kind of scenario. Okay, so let's talk about the domains of these things. Okay, if this function, let's say G was, Yep, they are. It's just called a bean graph.
Actually?
No, that's the dumbest thing I've ever heard. So let's say G was 1 over x plus 3. Okay, and I ask you to choose x to be negative 3. What happens? Divide by 0. Can't do it, right? So my output becomes undefined, right? So my output becomes undefined. Therefore, there's nothing that I can run through my next function f, right? So the idea, if I'm trying to figure out the domains of f of g of x, find my final composite domain, I first have to understand what the domain is of my innermost function. I have to understand my domain for 1 over x plus 3 in this case. Okay? The second thing you have to do is when you're done, you have to figure out what is the domain of the end result. Okay? So right here it says the domain of f composite g is a set of all x in the domain of g such that g of x is in the domain of f. I think that's confusing. The domain of f composite g is a set of all x in the domain of g such that g of x is in the domain of f. That's how it's expressed in every single math textbook on how to figure out the domain of your composite functions. The way we interpret that, what that really means is f composite g of x is defined whenever g of x, your innermost function, has to be defined. That's that first thing I just showed you with the 1 over x plus 3. So your first value, you have to be able to get a first output, right? You need to choose an input that gives you a first output. If that doesn't happen, then f of g of x is not going to be defined there. Okay? So f of g of x is going to be defined wherever the first input is defined, so g of x, wherever that's defined, and where f of g of x are defined. So this word and means what? Intersect. Okay, talking about domains here. Okay, not probabilities. Okay, so
I get.
you said multiply.
I get bullied for being the only one that answers.
I'm just saying. I'm not bullying you. So g of x and f of g of x are defined at a domain where g of x and f of g of x's domains overlap. Okay? So when we look at, let's just do a few examples here. This one's kind of easy. If I look at x squared and x minus 3, what's the domain of both those? What's the domain of f? All the numbers. What's the domain of g? All the numbers. Okay, so when I find g composed of f of x, which is going to be g of f of x, okay, let's see what this looks like. So f of x is x squared, right? Okay, so now I'm going to take x squared and go over to g, and wherever I see my variable, I'm going to replace it with x squared now, right? So it becomes x squared minus 3. Now, the domain of f, or not f, g of f of x is intersection of f of x's domain and g of f of x's domain. Does that make sense? So there's your what is f of x's domain? All real numbers. So that is negative infinity to infinity. And now we got to look at our final production. We got to look at x squared minus 3. What's x squared minus 3's domain? All real numbers. So what is the domain of my composite function? The overlap of those two things. So it'd be all real numbers again, right? Does that make sense to everybody? They're both polynomial functions. So their composite is polynomial. So then if they both had initially a all real number domain, then their composite has an all number domain. Let's see if there's one here.
Every time I hear say this part, I feel like it's when they used to bring like the pizza and the pickles down in elementary and ate your classroom, like a pizza party. You guys don't, Sarah, you wouldn't know. But you guys don't remember that when it's pizza party?
That didn't happen for everybody. They try to keep you separate from everybody else. And, you know.
Like, no, pickles. Listen, pickles, the pizza, and like it was really bad pizza, but like, you do? And like they used to bring it up down on a big card. Yeah. Okay, thank you.
All right, let's find g of f of x. Okay. So we're going to take g of, so f of x is 4th root of x, right? Okay. So now I'm going to take that as my input into x plus 9. So it's going to look like 4th root of x plus 9. Does that make sense?
Yeah.
That right there is g of f of x. Now, I've got to ask my question about what is the domain. So I'm interested in what is the domain of that thing first. No, it's not. F of x is a root function, right? It's an even root function. So you can only take even root functions of 0 to infinity, right?
Correct.
Okay.
Correct.
Otherwise, I get I. Then you have to look at this one, and that is the same domain. So then we look at the overlap, and the overlap would be that domain, right? Okay. There are 2 assignments in WebAssign. One's due Wednesday, one's due Thursday. The one due Thursday we'll talk about tomorrow, but you should be able to finish the one due Wednesday.
Okay. Have a good day.
You too.